Welcome to the video lecture on isomerism in coordination compounds. At the end of this session, students will be able to discuss isomerism in coordination compounds and identify the types of isomerism in the given coordination compounds. An outline of isomerism in coordination compounds is shown here. We will discuss each type of isomerism in detail. We will start with structural isomerism. There are three types of structural isomerism exist in coordination compounds. They are ionization isomerism, coordination isomerism, and linkage isomerism. We'll start with ionization isomerism. Ionization isomers occurs when a ligand that is bound to the metal center exchanges places with an anion or neutral molecule that was originally outside the coordination complex. Here, two examples are given. The difference between the ionization isomers can be viewed within the context of the ions generated when each are dissolved in solution. For example, when pentamine bromo cobalt chloride, which is the second compound, if it is dissolved in water, chloride ions are generated because chloride ions are outside that coordination sphere. Whereas when the first compound, pentamine chloro cobalt 2 bromide, is dissolved, bromide ions are generated. Reason, the bromide ions are outside the coordination sphere. Solvate and hydrate isomerization. It is a special type of ionization isomerism. A very similar type of isomerism results from replacement of a coordinated group by a solvent molecule. Then we call this type of isomerism as solvate isomerism, which if the water is the solvent, we will call it as hydrate isomerism. Three compounds are given. The formulas are given here. We can see that all these compounds are showing different color and they are different compounds. These isomers have very different chemical properties, and on reaction with silver nitrate to test for chloride ions would find 1, 2 and 3 chloride ions in solution respectively. We can see the number of chlorine atoms outside the coordination sphere which would find 1, 2, 3 chloride ions in solution. Waters of crystallization. Upon crystallization from water, many compounds incorporate water molecules in their crystalline framework. These waters of crystallization refers to water that is found in the crystallization framework of a metal complex or a salt which is not directly bonded to the metal cation. If you see here, in these three compounds, see the number of water molecules associated with their structure. In the first compound, 2 water molecules, second one, 1 water molecule, and the last one, no water molecule outside the coordination sphere. Second type of isomerism is coordination isomerism. Coordination isomerism occurs. Compounds containing complex anionic and cationic parts can be thought of as occurring by interchange of some ligands from the cationic part to the anionic part. Here we can see one example. The first one, tetramine zinc 2 tetrachlorocuprate 2. Second one, tetramine copper 2 tetrachlorosincate 2. We can see here, in the cationic entity, the ligand is ammonia, which is attached to the zinc central metal atom. Chloride ligands attached with the copper central metal atom. But in the second compound, ammonia ligand is attached to the copper central metal atom and chloride ion with the zinc metal atom. So we can see here exchange of ligand. Previously in this case, for zinc, Ammonia was the ligand. Here, for zinc, chloride ion is the ligand. Another example shown here. In this complex, ammonia ligand is for the central metal atom copper and cyanide group for the central metal atom chromium. Here it is exchanged. For ammonia, it is attached to the chromium central metal atom or ion, and cyanide ligand for central metal ion cobalt. Third type of isomerism is linkage isomerism. It occurs with ambidentate ligands that are capable of coordinating in more than one way. So ambidentate ligands such as SCN, NCS, nitro, these groups are ambidentate ligands which can coordinate to the central metal atom in more than one way. The only difference is what atoms, the molecular ligands, bind to the central ion. Here you see nitro group. Here nitrogen will be attaching, or nitrogen will form the bond with the central metal atom. In this case, in the nitrito, even though the formula is NO2, here oxygen atom is going to undergo a bond between the central metal atom or ion. Example is given here. The cationic cobalt complex CONH3 5 times NO2 Cl2 exists in two separable linkage isomers of the complex ion. The first case here in this compound is a nitro isomer. Reason here nitrogen atom is attached to the central metal ion or atom cobalt. In nitrito isomer, oxygen atom is attached to the central metal ion which is cobalt. So both are isomers, they are linkage isomers. Why they called as linkage isomers? Because they contains ambidentate ligand where the coordinating atom will be different. Second types of isomerism, that is stereoisomerism. Two types of stereoisomerism we have to study. First one, geometrical isomerism. Second one, optical isomerism. We will discuss in detail. Geometrical isomerism. Metal complexes that differ only in which ligands are adjacent to one another, that is cis, or directly across from one another, that is trans, in the coordination sphere of the metal are called geometrical isomerism. So one more time I will give the definition. Metal complexes that differ only in which the ligands are adjacent to one another, that is cis isomer, or directly across from one another, trans isomers, in the coordination sphere of the metal are called geometrical isomers. They are the most important, among these most important both for square planar and octahedral complexes. Normally no geometrical isomerism present in tetrahedral structured complex. The reason, tetrahedral complexes do not show geometrical isomerism because the relative positions of the unidentate ligands attached to the central metal atom are the same with respect to each other. So there won't be any difference in their structure if they change their relative position. But in square planar complexes shows geometrical isomerism. In square planar complexes, no geometrical isomerism for Ma4 complexes. So in square planar complexes, if all the ligands are same, that's why we call it as Ma4. M stands for the metal and A stands for the ligands. All ligands are same, then there will not be any geometrical isomerism. Reason, because in Ma4 complexes, all vertices of a square are equivalent. It does not matter which vertex is occupied. So there will not be any geometrical isomerism for Ma4 complexes. No geometrical isomerism for Ma3b complexes. So Ma3b complexes also there won't be any geometrical isomerism, because if you draw the structures of the square planar complex Ma3b and you are giving the relative position, you are changing the relative position of the ligand B, but they are all equal because all vertices of a square are equivalent. It does not matter which vertex is occupied the ligand B in a square planar Ma3b complex. All four structures shown here are chemically identical because they can be superimposed simply by rotating the complex in space. So if you rotate the structure, we can actually we can superimpose those structures by rotating the complex in the space. So all are chemically identical. For an Ma2B2 complex, so two types of ligands, and the numbers will be 2 each. For an Ma2B2 complex, there are two possible isomers. Either the A ligands can be adjacent to one another, that is cis, in which case the B ligands must also be cis, or the A ligands can be across from one another, in which case the B ligands must also be trans. So here we can see cis isomer and trans isomer. Here we can see here the ligand BB, they are together, they are adjacent to each other, adjacent to each other, adjacent to each other, adjacent to each other. So these are Ma2B2 square planar complex cis isomer. If they are in opposite direction or across, for example here B, B, they are across, B, B, they are across. So this isomer is known as trans isomer. So for an Ma2B2 complex, two possibilities of geometrical isomerism. Either the A ligands can be adjacent to one another, cis, it's shown here. A ligand can be across from one another, trans isomer, that's shown here. One of the best known examples for cis and trans isomers of an Ma2B2 square planar complex is cis-platin. Formula is cis platinum NH3 twice and Cl2. It's also called cisplatin. And transplatin, platinum NH3 twice Cl2, which is actually toxic rather than therapeutic. So cisplatin is used for used in medical application when transplatin, which is toxic and it cannot be a therapeutic. So structures are given here. Cisplatin and transplatin. In cisplatin, the identical groups or the same group are adjacent to each other. In transplatin, they are across each other. So in geometrical isomerism, in Ma4 complexes, no possibility of geometrical isomerism. In Ma3B complexes, no geometrical isomerism is possible. But in Ma2B2 complex, there are two possible geometrical isomers, cis and trans. Now geometrical isomerism in octahedral complexes. Octahedral complexes also exhibit cis and trans isomerism. But geometrical isomerism is not possible for Ma5B complex, means only one structure is possible for Ma5B. But in Ma4B2, two isomers are possible. Here, we can see here, identical groups are across each other, trans, and here they are adjacent, so cis. So in Ma4B2 complex, two isomerism possible, cis and trans. One example is given here. Geometrical isomer cis and trans of CONH3 4 times Cl2. So it is an Ma4B2 type of octahedral complex. Here, two chlorine atoms, the identical groups are adjacent to each other, and here the identical groups are opposite to each other. Geometrical isomerism in octahedral complexes, we will take another example for Ma3B3 complex. There are also two possible isomers. In one, three ligands of each kind occupy opposite triangular faces of the octahedron, and this is called FAC isomer, for facial isomer. In the other, three ligands of each kind lie on what would be the meridian if the complex were viewed as a sphere. This is called MER isomer or meridional isomer. So here we can see three ligand, same ligand, they occupy in triangular faces. You see, if I join all these things, we will get a triangle. So it's a triangular faces of the octahedron structure. So that's why this isomer is known as facial isomer. In the other, the 3 ligands. In another isomer, see B, B, B. So they lie on meridian if the complex were viewed as a sphere. So this is called meridional isomer. So they actually lie on the meridian if we consider the complex, or if you view the complex as a sphere. That's why we call it as meridional isomer or mer isomer. One example is here given here. CONH3 thrice, NO2 thrice. So it is Ma3B3 structure. 2 types where the identical group nitro group, they are in occupy opposite triangular faces, and the same time here NO2, NO2, NO2. They lie on what would be called meridian if the complex were viewed as a sphere. This is called mer isomer. Geometrical isomerism in octahedral complex. Another example is given here. COCl2En twice. So here ethylene diamine, which is a bidentate ligand. So total 2 plus 4, 6 octahedral complex. So 2 types of isomers, cis and trans isomer. Here we can see the identical groups are opposite to each other in trans, and here the identical groups are adjacent to each other. So we call it as cis isomer. Another example, FeNH3 twice CN4 minus. Here the similar group, they are adjacent to each other, cis structure, and the similar groups which are opposite to each other, adjacent to each other in cis and opposite to each other in trans. Some practice problems. So after listening this class, you should be able to answer all these questions. Indicate the types of isomerism exhibited by the following complexes and draw the structures of these isomers. First one, so you have to indicate the types of isomerism exhibited by the following complexes. Will you be able to draw any structural or geometrical isomerism of these kind of compounds? Another example, give evidence that CONH3,5Cl SO4 and CONH3,5SO4Cl are ionization isomer. Which experiment that you can perform to check these 2 compounds are ionization isomers? Hint I will give, when you dissolve so this compound, we know that the sulfate ion will be ionized, and here the chloride ions will be ionized and go into the solution if you dissolve it in water. Another example, another practice problem, how many geometrical isomers are possible in the following coordination entities? CrC2O4 thrice, 3 minus, CONH3 thrice, Cl3. How many geometrical isomers are possible in the following coordination entities? Whether they will show cis and trans isomerism, you have to check. Draw the cis and trans isomers of the following compounds. 3 compounds are given. You should be able to draw the cis and trans isomers of these compounds. Last type of isomerism that we will be studying in this class is optical isomerism. Optical isomers are mirror images that cannot be superimposed on one another. These are called enantiomers. The molecules or ions that cannot be superimposed are called chiral. The 2 forms are called dextro and levo, depending upon the direction they rotate the plane of polarized light in a polarimeter. So if you are passing a polarized light, in which direction the compound shifts, the radiation of the direction of the light, based on that we can call that isomers as dextro or levo. If it is rotating to the right, then we will call it as dextro, and we will be giving the notation small letter d for it. And if it is rotating to the left, then we will give the notation L for it. Optical isomerism is common in octahedral complexes involving didentate ligands. So optical isomerism is very common if in octahedral complexes where didentate ligands exist. For example, ethylene diamine. So optical isomerism is common in octahedral complexes involving didentate ligand. Here we can see COEN3 thrice, 3 plus. If you take this structure and you take its mirror image, now try to superimpose its mirror image on the first image. Definitely they are non-superimposable. If they are non-superimposable, so we can call it as enantiomer. And if we perform the test using polarimeter to find in which direction these compounds shifts the direction of the light, this compound, it will rotate to the right, that's why it's called dextro, and this compound, this isomer, will shift the direction of the light to the left. By checking the structure, you will not be able to tell whether it will be dextro or levo. For that, we have to perform the experiment with the help of polarimeter. Then only we will be able to tell in which direction each isomer will shift the direction of the light. Another example, PtCl2En2, 2 plus octahedral complex with 2 didentate ligand. Here we can see one structure and its mirror image. Try to superimpose mirror image with this image. We know that they are not superimposable. If they are not superimposable, they are enantiomers. Then if you perform an experiment with the polarimeter, then we will be able to find which direction these compounds shift the light. So this compound, it will shift the direction of the light to dextro. This observation, we can find it only after performing the experiment. And this isomer, this isomer, which will rotate the light into the left direction, that's why we call it as levo. So what is an enantiomer? A pair of enantiomers consists of 2 molecular species which are non-superimposable mirror images of each other. For example, if you are passing a plane polarized light through a polarimeter tube which contains a solution of the isomer, solution of the compound that you have taken, and you see in which direction it rotates. If it is rotating to dextro, then we will call it as D. If it is rotating left, then we will call it as L. Now, not only the direction, what is the angle? The characteristic angle, that means the instrument is used to measure the rotation is called polarimeter. So polarimeter will check how much angle it actually rotated. The light is shifted to a particular direction. How much angle? That angle we call it as alpha. It will be represented alpha degree. So if it is rotating, if it is rotating clockwise, we will take it as positive, and if it is rotating anti-clockwise, we will call it as negative alpha degree. The rotation alpha is measured in polarimeter. In practice, the amount of rotation depends upon the wavelength of the light, temperature, and concentration of the compound present in solution. The specific rotation alpha for a chiral compound in a solution is given using this equation. Alpha equal to the specific rotation. This alpha equal to alpha. Alpha is the angle that we measured in polarimeter divided by C, that's the concentration in grams per centimeter cube, and L is the path length of the solution in polarimeter, that should be in decimeter. Small description about enantiomers, plus and minus prefixes. So sometimes we will give instead of D and L, in addition to D and L, or instead of D and L, we will use plus and minus prefixes. The specific rotation of enantiomers is equal and opposite, and a useful means of distinguishing between enantiomers is to denote the sign of alpha. Thus, if two enantiomers of a compound A, we show that alpha value as plus 12 degree and minus 12 degree. So we will write it as plus means which rotates the light towards clockwise direction, and minus means the angle at which if it is rotating in anti-clockwise direction. Sometimes plus and minus are denoted by dextro and levo, and this refers to right and left-handed rotation of the plane polarized light. Dextro and levo are generally abbreviated to D and L. The plus or minus or D or L notation is not a direct descriptor of the absolute configuration of the enantiomers, the arrangement of the substituents or ligands for which the following prefixes are used. Examples. Out of the following two coordination entities, which is chiral, that is optically active, first structure, CrCl2 OX2 3 minus, then trans. So we have to check whether these compounds, whether these isomers, they are optical isomers, right? Whether each isomers, whether they show, they are geometrical isomers, whether they show optical isomerism or not. So first we have to draw the structure of the first compound, that is cis, we have drawn, take its mirror image. If that mirror image is not superimposable with this image, then we can call that it has an enantiomer. Then if it has an enantiomer, there is a great chance that it will show optical isomerism, or it will be optically active. At the same time, you take the trans CrCl2OX2, take its mirror image. We know that the mirror image will superimpose with this, so definitely this cannot be an optically active compound because it won't be having any enantiomer. Practice problems. Draw the structures of optical isomers of CrC2O4 3 minus, PtCl2En2 2 plus, CrNH3 twice Cl2En plus. So they draw the structures of optical isomers. Explain why CS6 COEN2 Cl2 plus is chiral while trans COEN2 Cl2 plus is achiral. Simple. We have to draw the structure, then see is there any superimposable mirror image for this structure. If it is there, then definitely if it is a non-superimposable mirror image is there, then definitely it will show optical activity, and it will have a chiral carbon atom. If the mirror image is superimposing, then definitely it will not be showing any enantiomer and it will be optically inactive. Give formulae for the compound that are coordination isomers of COBPY 3 plus and FeCN6 3 minus. What other types of isomerism would be exhibited by any of the complex ions given in your answer to the part A? For this question, what are the other types of isomerism would be exhibited by any of the complex ions given in your answer to the part A? What isomers would you expect to exist for platinum 2 compounds? These two compounds. What type of isomerism that you can expect? How many different forms of COEN3 3 plus are possible in principle? Indicate how they are related as enantiomers and diastereo isomers. Draw all the isomers, geometrical and optical, of the given compounds. Write all the geometrical isomers of PTNH3, Br, Cl, Py. And how many of these will exhibit optical isomerism? So these are the practice problems that you have to solve. Next, summary. 2 categories of isomerism in coordination compounds: A, structural isomerism; B, stereoisomerism. In structural isomerism, 3 types of isomerism exist. 1, ionization isomerism; 2, coordination isomerism; 3, linkage isomerism. In stereoisomerism, 2 types of isomerism: 1, geometrical and 2, optical isomerism. Thank you. Next topic is valence bond theory in coordination compounds. In this session, we will study about valence bond theory in coordination compounds and predict structure and properties of coordination compounds using valence bond theory. Coordination compounds contain complex ions in which ligands form coordinate bonds to the metal. Thus, the ligand must have a lone pair of electrons and the metal must have an empty orbital of suitable energy available for bonding. The theory considers which atomic orbitals on the metal are used for bonding. From this, the shape and stability of the complex can be predicted. According to this theory, the metal atom or ion under the influence of ligands can use N-1d, Ns, Np orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planar and so on. These hybridized orbitals are allowed to overlap with ligand orbitals that can donate electron pairs for bonding. Here the number of orbitals and types of hybridizations are given. If the coordination number is 4, two types of hybridization and two types of distribution of hybrid orbitals in space can be obtained if the coordination number is 4. If it is following sp3 hybridization, then it will be tetrahedral. If the coordination number is 4 and the hybridization is dsp2 type, then the shape of the complex will be square planar. If the coordination number is 5 and the hybridization is sp3d, then the distribution of hybrid orbitals in space or the shape of the complex ion or complex molecule will be trigonal bipyramidal. If the coordination number is 6 and the hybridization is sp3d2, then the shape will be octahedral. And if the types of hybridization is d2sp3, then also the shape of the hybrid orbitals or distribution of the hybrid orbitals in space is octahedral. If we know the magnetic property of a coordination complex, then we can predict the geometry of a coordination. Predict the geometry of diamagnetic octahedral complex CONH363+. So this complex is diamagnetic in nature. So if we measure the magnetic property of this complex, we will get that property as diamagnetic in nature. Here the central metal ion is cobalt 3+, and we know that cobalt is having an atomic number of 27, where it follows an electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. But here the charge of cobalt ion is 3+, so 3 electrons should be removed from cobalt atom, and the new electronic configuration of this ion will be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6. And if we arrange these electrons in the respective orbitals, we will get in 3d 6 electrons, 4s and 4p, they are vacant. Now in this complex, 6 ammonia ligands are joining. 6 ammonia ligands, if they come, it requires 6 vacant orbitals in CO3+ for coordinate bonding. So definitely in that case, if you see 3d orbitals do not contain any vacant orbital. So for vacant orbital, we have to look for 4s, 4p and 4d. But if that hybridization is occurring, then there will be electrons in the orbitals which are not paired. At that case, the property of that complex should have been paramagnetic because there are unpaired single electrons. But we know that CONH363+ is diamagnetic in nature. How is it possible? There is no vacant d orbitals in 3D, so usually it cannot take part in the bonding. Then the complex will be paramagnetic, but the magnetic property given is diamagnetic in nature. So it is necessary to have internal pairing. So it is necessary to have internal pairing in 3D orbitals like this. These electrons shifted to the inner orbitals and you can see now there are now 2 3D orbitals which are free. So now total 2 3D orbitals, 1 4s orbital, 3 4p orbitals. Now 6 vacant orbitals are there now. So coordinate bonds with the 6 ammonia ligands are possible now. So these orbitals undergo D2sp3 hybridization. We can call it as an inner orbital complex because in addition to the outermost 4s and 4p orbitals, so you see the type of orbitals which undergo the hybridization, one is 4p, then 4s. They are outermost orbitals, and 1 or 2 orbitals from 3D which is inner orbital. So we call this complex as inner orbital complex because 2 d orbitals from the inner shell took part in this hybridization. So here the complex can be named as an inner orbital complex because in addition to the outermost 4s and 4p orbital, the inner 3d orbitals took part in the bonding. Complex ion is diamagnetic and a low spin complex. Since it is D2sp3 hybridization, the structure of the complex ion is octahedral. Next example, predict the shape of paramagnetic high spin complex COF6 3- ion. So we have to find the shape of this molecule or this ion And we know that by measuring its magnetic property, this ion shows paramagnetic nature. Again, the central metal atom or ion is cobalt, where its oxidation, where its atomic number is 27. Here it is CO3 plus. So definitely 3 electrons will be removed from the cobalt atom, and the electronic configuration of CO3 plus is 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6. So electrons are arranged in the respective orbital. Here the complex is high spin complex and paramagnetic. So see the nature of this complex. It's a paramagnetic nature. Paramagnetic in nature means if there are single electron occupied orbitals, no problem, because then it will show paramagnetic nature. 6 fluorine ions are joining. 6 fluorine ions are joining means how many vacant d orbitals, vacant orbitals in the central metal atom or ion is required? 6. How the 6 will come? 1 from 4s, 3 from 4p, and 2 from 4d. So total 6 orbitals. Here why internal pairing is not required? Because the complex is paramagnetic in nature. So internal pairing is actually not required. So from where we will get 2 vacant orbitals other than 4s and 4p? It's from 4d. 2 d orbitals from 4d will also be taking part in the hybridization. So these 6 orbitals, they will undergo hybridization and form 6 hybridized orbitals, and these 6 hybridized orbitals will be interacting or will be forming the coordinate bond with the ligands, which are 6 fluoride ions. So here the hybridization is sp3d2 hybridization, since here the outer 4d orbitals are taking part in the bonding. Here outer d orbitals are taking part in the bonding, so it is outer orbital complex. Since 4, here you can see 4 single electron occupying d orbitals are present, it is high spin paramagnetic complex. High spin paramagnetic complex. Sorry, it's not diamagnetic, it's the paramagnetic complex. Example 3, predict the shape of paramagnetic NiCl4 2-. Here the oxidation is the charge of nickel ion is +2. Oxidation state of nickel is in this charge is +2. Therefore, the electronic configuration of nickel ion is 1s2, 2s2, 2p6, 3s2, 3p6, 3d8. And we know that this complex ion is paramagnetic in nature. One more information we have. So if I arrange these d electrons in 3d orbitals, we will get 2, 2, 4, plus 2, 6, plus 1, 7, 1, a total 8 electrons are present. Then vacant 4s orbital, vacant 4p orbital. Now, how many ligands are joining? 4 chlorine ligands or 4 chloride ligands, 4 chlorine ligands are coming. So here chloride ligands only 4, so it requires only 4 vacant orbitals for the central metal atom. So we will check, is there any vacant 4 orbitals? Yes, 1s and 3p. So here internal pairing is actually not required. The reason because it is paramagnetic, so it's not necessary to there is no need for internal pairing of the electrons present in 3d orbitals. Since it is paramagnetic complex ion, no internal pairing is required. So 1 4s orbital and 3 4p orbitals are ready for hybridization, which leads to sp3 hybridization. So how many sp3 hybridized orbitals will be forming? sp3, so 1s, 3p. So total 4 sp3 hybridized orbitals will be there. These hybridized orbitals will be interacting or will be forming the bond between the ligand. Since it is paramagnetic complex ion, no internal pairing is required. So 1 4s orbital and 3 4p orbitals are ready for hybridization, which leads to sp3 hybridization, and the geometry is tetrahedral. complex ion is paramagnetic in nature. Last example. Predict the shape of the diamagnetic NiCN4 2- complex ion. Again, nickel oxidation state is +2 here. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d8 is the electronic configuration for nickel ion. And we can arrange those 8 electrons in 3d orbitals, and we have 4s and 4p vacant. Now we know that the property of the magnetic property of this complex is diamagnetic, so there should not be any single electron occupied orbitals, but we have 2 here. So in order to get the diamagnetic nature explanation properly, we know that there should be an internal pairing happens inside the 3d orbital. So 1 electron in the 3d orbital goes into the this other single occupied d orbitals. Now we know that 1 d orbital is free, 1 4s orbital is free. Now 2 more free vacant orbitals are required, so that will be from 4p. So 1 3d orbital, 1 4s orbital, 2 4p orbitals, total 4 orbitals. These orbitals will undergo hybridization from dsp2 hybridized orbitals. So total 4 dsp2 hybridized orbitals will be there, and those will be taking part in the bonding. Here the geometry is square planar and the complex ion is diamagnetic in nature. Now, what are the limitations of valence bond theory in coordination chemistry? It involves a number of assumptions. It does not give quantitative interpretation of magnetic data. It does not explain the color exhibited by coordination compounds. It does not give a quantitative interpretation of the thermodynamic or kinetic stabilities of coordination compounds. It does not make exact predictions regarding the tetrahedral and square planar structures of 4 coordinate complexes. It does not distinguish between weak and strong ligands. These are the limitations of the valence bond theory in coordination compounds, and these limitations we can actually overcome with the help of molecular orbital theory or crystal field theory that we will study later. Here is actually a table where, if you know the coordination number, we will be able to find what kind of hybridization it follows, and few examples of those compounds having those kind of hybridization and coordination number. Now, some important things to remember in this valence bond theory. Coordination compound contains complex ions in which ligands form coordinate bonds to the metal. Thus, the ligand must have a lone pair of electrons and the metal must have an empty orbital of suitable energy available for bonding. The theory considers which atomic orbitals on the metal are used for bonding. From this, the shape and stability of the complexes are predicted. The theory has mainly 2 limitations. Most transition metal complexes are colored, but the theory provides no explanation for their electronic spectra. Further, the theory does not explain why the magnetic properties vary with temperature. For these reasons, it has largely been superseded by the crystal field theory that we will study in the future classes. However, it is of interest for study as it shows the continuity of development of modern ideas from Werner's theory.